I would like to thank the organizers for giving me a chance to talk about work that has been mainly done by my student Giorgos Ioannidis on jet formation in barotropic turbulence. Now, you've seen this slide before today as well, and I don't think it takes much effort to convince you that geophysical turbulence is observed to be self-organized into large-scale structures in nature and in laboratory flows. The difference between the morning talks and this talk is that the large-scale structure is not a vortex. We are talking about zonal jets that you can see with these banded structures in the Jovian atmosphere. Now, a typical model that retains the relevant dynamics in this case is stochastically forced barotropic flow on a beta plane in a doubly periodic box. The dynamics is the conservation of absolute vorticity in the absence of forcing and dissipation. Turbulence is sustained by this random steering psi that we consider to be delta correlated in time, to be spatially homogeneous, and we normalize it to inject energy at a rate epsilon. There's also linear dissipation so that we reach a statistical steady state. And we will consider two cases for the spatial structure of the forcing. We'll consider an isotropic forcing, and you can see its realization in physical space on the right here. And we will also consider an anisotropic forcing that sort of mimics baroclinic instability in the sense that the waves that we force here have a meridionally elongated structure, just as the unstable modes in baroclinic atmosphere are. So what has been observed is that you get a rapid regime transition in the flow when you increase the energy input rate of the forcing, or the amplitude of the forcing if you like. And you can quantify this transition by calculating the energy going into zonal modes, so going into zonal jets, divided by the total energy in the flow. And by calculating this index, termed here as ZMF, you can plot it as a function of the energy input rate. And you can see that nothing happens until you pass this critical threshold. So the flow remains homogeneous and isotropic if you force with isotropic forcing. And once you pass this critical threshold, you can see that the ZMF index rapidly increases. And if you look at the flow, you see zonal jets emerging. And you can see them in this Hofmöller plot showing the zonally average zonal velocity, where you can see the emergence of jets and the eventual setup of 3 jets in this case. Now, since this is a very abrupt transition, this points towards bifurcation or a phase transition, as we've also heard earlier. So how can we deal with this, since this is a fully turbulent flow? The key observation here is that the jets are maintained by the collective action of all the eddies in the flow, pointing towards collective instability. And the way to study this is to study the evolution of the statistics of the flow. So way forward is to study the so-called statistical state dynamics. Now, of course, we have the usual turbulence closure problem, so we have to approximate this system at a certain order. It has been shown that for this particular case, a second order closure of the statistical state dynamics captures very well this transition, and you will see this in a couple of slides as well. Now, 2 of these closures are the stochastic structural stability theory and the second order cumulative expansion. These come in various flavors and versions. The one that we are going to use is the following. we split the flow in a zonally averaged jet, denoted by the overbar, and prime quantities, which are the non-zonal eddies, denoted by the primes here. And you can write down the equations governing the interaction of the zonal jets with the non-zonal eddies. Now, if you ignore the eddy-eddy interactions that cascade energy locally in wave number space, you end up having a quasi-linear dynamics. And if you calculate the statistics of these quasi-linear dynamics, you get a system closed at second order. So the mean, the statistical mean, or the first cumulant, is just the zonal flow here. And this, of course, is forced by the eddy fluxes. The eddy fluxes are a function of the eddy covariance. And if you write down the equation for the evolution of the eddy covariance, this does not involve higher order cumulants or moments, because the eddy-eddy interactions are absent. So we end up having this closed system evolving the statistics of the flow. Now, there is a fixed point for this dynamical system. It's homogeneous, so there's no mean flow, and the covariance is proportional to the forcing covariance, so it's homogeneous. And it turns out that this homogeneous fixed point is stable when the energy input rate is below a certain value, and becomes unstable when you pass this critical value. And the emergence of the instability is nothing more than these zonal jets. Now, as you can see from these figures, comparing the evolution of the statistics closed at second order to the direct numerical simulations of the fully turbulent dynamics, you can see that jet formation is accurately captured, whether you're looking at the ZMF index or whether you're looking here at what the actual flow looks like. So jet formation is due to this instability that has been termed as zonostrophic. It has been studied numerically by Farrell and Ioannina, and analytically by Srinivasan and Young. Its equilibration has also been studied by Parker, Kromes, Constantino, and other workers. So our goal here is to trying to shed light into the eddy-mean flow dynamics underlying this instability. And we're going to use a geometric approach. And by geometric, I'm literally saying geometric. It's a framework developed by David Marshall and co-workers that's based on an older idea by Brian Hoskins. It's an acronym, stands for Geometry and Eddy Energetics of Ocean Mesoscale Eddies and their Rectification and Impact on Climate. Wonderful, huh? So the idea is the following. The eddy fluxes can be written as a divergence of the eddy stress tensor. This has the momentum fluxes in its diagonal and a term that has to do with the isotropy on the flow in its anti-diagonal. And you can rewrite this stress tensor in terms of three other parameters. One is dimensional, it's the eddy kinetic energy, and the other two are non-dimensional. There's this parameter gamma related to the isotropy of the flow, and there is this angle theta. Now, if you write the tensor this way, you can also visualize it in terms of an eddy variance ellipse. And the ellipse characteristics are related to these three parameters. And of course, they are related to properties of the eddies. So the angle theta is the angle of the semi-major axis of the ellipse, and represents the eddy tilt in the flow, so how eddies tilt in the flow. The eccentricity of the ellipse is related to this anisotropy parameter gamma, and gamma takes is between two values, between 0, where the ellipse is a circle and the flow is isotropic, and 1 is the other limiting value where the ellipse is a straight line and the flow is highly anisotropic. And the focal point, or the area of the ellipse, if you like, is related to the eddy kinetic energy. So since the eddy fluxes are related to the gradient of the tensor, the eddy fluxes are related to gradients of these 3 parameters. So you get a few patterns on how the ellipse changes with latitude, and changes in this pattern, in these patterns, bring about flow acceleration or deceleration. So a few of these patterns are shown here. For example, if the angle is in the first or third quadrant and the ellipse shrinks with latitude, then this causes an eastward acceleration to the flow. Similarly here, if again the angle is in the first quadrant and the ellipse, the eccentricity decreases so that the flow gets isotropized with latitude, then this again causes an acceleration for the flow. Finally, if the angle is in this sector and turns clockwise as we move in latitude, then this again causes an eastward acceleration. So by looking at this ellipse and how it changes in space, we can deduce the forcing of the eddies to the mean flow, and we can also relate this to their properties. So we did exactly this regarding the zonostrophic instability. First, in the linear phase, where the linearized dynamics, the normal modes in this case are harmonic, and the growth rate increases with the energy input rate. So there is a certain value where the most unstable mode, having a wave number n sub c here, is right at the stability boundary. So we examine the instability right here at its onset. So from the covariance for the unstable mode, for the most unstable mode, we can calculate analytically the properties of the ellipse and how these change with latitude. So for the case of non-isotropic forcing, what we find is the following. The anisotropic parameter and the eddy kinetic energy are constant to leading order. So the flow is accelerated due to changes in the angle of this ellipse. And an illustration of how the angle changes is shown here, where you can see the ellipse in various latitudes within a wavelength for the most unstable jet. And you can see the 2 patterns here. On the left flank of the jet, you can see a counterclockwise rotation for the angle, causing an eastward acceleration. And on the right flank, we have the opposite. We have the angle in this sector and rotating clockwise. And also, it is very nice that in a certain limit, so for low values of beta, you can also parameterize the angle since the angle is proportional to the shear. So that in this limit, the eddy vorticity fluxes act exactly as negative diffusion. Now, for isotropic forcing, things are a little bit more tricky. We have the jet accelerated due to changes both in the angle and in the isotropy parameter. The angle is plotted on the left here, where you can see that it's piecewise constant. The reason is that in this case, the momentum fluxes are much larger than this isotropic parameter, so that the angle is an odd multiple of pi over 4. The only places where you have sharp gradients for the angle are right here where the jet core is. Now, the anisotropic parameter, as you can see, has positive values, which means that the isotropic eddies are anisotropized by the emerging jet. everywhere except here near the jet cores. So how does the ellipse look like? It looks like this, where you can see again these two patterns. On the left flank of the jet, the eddies tilt with the shear and get isotropized as we move to the jet core. And the opposite happens. Again, the eddies tilt with the shear on the right flank of the jet and get anisotropized as we move away from the jet core. Both of these lead to an eastward acceleration. And as was described earlier, the bulk of the jet is accelerated due to changes in the eddy isotropization. So as the eddies get anisotropized, they accelerate the flow, whereas right at the jet cores, the jet is accelerated due to the change in the eddy tilt. And in the same limit as before, the addition of these two terms acts exactly as a negative hyperdiffusion. Now, regarding the equilibration of this instability, we have examined it in the weakly nonlinear limit, where we are close to the onset. So the energy input rate is the critical value plus a small parameter times this value. And in this case, as you can see, the growth rate is of order mu squared, so it's small. And there is also a band of wave numbers close to this most unstable wave number that get rendered unstable as well. This band has a width m, mu. So guided by this, we can look for solutions that have jets with the most unstable wave number and with an amplitude that is slowly evolving in latitude and time. Now, if you do a 2-time 2-scale analysis for the flow and do an order by order expansion here, you end up having circular terms that move away only if the amplitude of the jet satisfies Ginzburg-Landau equation. So we're going to use the GL dynamics to examine, in this case, again, the eddy variance ellipse, and we can calculate the eddy variance ellipse taking into account the nonlinear corrections. Since I'm a little bit out of time, this was just to convince you that the GL dynamics, which is the straight line here, does a pretty good job in approximating the fully nonlinear dynamics shown by the dots. And I'll move to the results for the non-isotropic case. Again, there is the flow is okay. The flow is accelerated due to the change in the angle, and the correction in the angle is proportional to the initial one, but has a negative sign, meaning that the changes in the eddy tilt are going back through the nonlinear correction. And for the isotropic case, as you can see, there are corrections in the anisotropy parameter and the angle, and the corrections are again as to reduce the initial action. So the eddies are re-isotropized, as it is shown by the negative values of gamma, and the gradients of the angle are reduced through this dipole structure. So since I'm out of time, I will leave you with the take-home messages, and thank you for your attention.
Maybe we can have one question while Grisha sets up. If there is one. Yeah.
Is it possible to get frictionless saturation of this tilting and amplitude mechanism?
We haven't tried this, no. Okay.
So let's thank Nico again.